Hello YouTube. In the previous video we examined the basics of Bayesian epistemology. Today I'd like to take a look at some of the criticisms of Bayesianism. So one of the points we raised in the previous video is that the Bayesian treats probabilities as degrees of belief. The axioms of the probability calculus are treated as rational constraints on degrees of belief. But the problem is that there are many ways in which degrees of belief and probability seem to come apart. So one big problem here is the logical omniscience problem. If our probability assignments are to conform to the probability calculus, then all logical truths must get probability 1. To deny logical truth is a contradiction. Logical truths are necessarily true. They could not possibly be false. So their probability must be 1. But in fact, there are many logical truths about which we are uncertain. Just consider all of the currently unproven mathematical conjectures. Some conjectures you might think are false, some you might be unsure about, some you might be quite confident that they're true. But the point is we have a whole range of different degrees of belief to different mathematical conjectures. But all of them are either necessarily false or necessarily true, right? So they all have either a probability of 0 or 1. And in fact, even when we consider the proven truths, it's not obvious that your degree of belief is 1, right? It's not obvious that you're certain. I mean, should you ever be certain that a logical or mathematical theorem is true or false? So, I mean, recall the Bayesian's connection, the Bayesian's definition of degrees of belief as having this connection with betting behaviour. You know, would you bet, for example, £10,000 on, say, the Pythagorean theorem for nothing in return? If you're certain that the theorem is true, you'd take the bet. But that seems pointlessly risky. I can think that a mathematical conjecture is true, which is to say I can think that the probability of the mathematical conjecture is 1 without being certain that it's true. So it seems like Bayesianism has trouble accommodating uncertainty about logical and mathematical truths. And surely uncertainty is often reasonable. Indeed, uncertainty is unavoidable for the many truths currently unproven. So one response to this is to say, well, Bayesianism is a model of ideal scientists, and obviously real-world scientists are not ideal. Ideal scientists would know all of the logical truths. The point of Bayesianism is we should aim to be more like the ideal. You know, we treat the idealization as a norm to which we aim. Now, of course, the question here is, well, all right, but why exactly is this, why take this as being the ideal? Why take sort of logically omniscient scientists as being the ideal rather than any other sorts of ideals we might make? So we might also assume as an idealization that scientists already have access to all possible evidence. So, we might assume as an idealization that scientists have a God's eye view of the universe. In that case, there would be no need to test theories because, the scientists would already know the outcome of every possible test. Obviously, this idealization wouldn't tell us much about how actual scientists behave or about the methodologies that actual scientists use. So, why then would we, make the idealization that scientists know all of the logical truths? I mean, perhaps the point here is, well, logical truths are not really relevant to scientific confirmation insofar as scientific evidence bears on hypotheses that could be false, right? So a theory of scientific confirmation is only going to concern contingent hypotheses, right? So it's only going to concern those truths for which we can acquire empirical evidence for or against. So maybe, it's not really a big deal to assume as an idealization that scientists know all the logical truths. So Bayesianism, despite this idealization, can still, elucidate specifically scientific reasoning. But all of this, of course, still leaves us with an important question. What exactly are the Bayesian probabilities, right? I mean, the main point here is that the Bayesian wants to say that probabilities are just degrees of belief. But it looks like the problem of logical omniscience shows that we can't simply identify one with the other. We can't say that, well, the probabilities just are degrees of belief. So here's another way to sort of press this concern. There are some hypotheses about which we are agnostic or noncommittal. So scientific anti-realists like Bas van Frassen are non-committal about all theoretical hypotheses that describe unobservables. If you've seen my series on scientific realism, you'll, be familiar with this kind of view. But we all have. There are going to be some hypotheses for all of us about which we are agnostic or non-committal. Now the question is, how do we represent this epistemic state in terms of probability assignments? Well, Van Frassen's idea, proposed in his book Laws and Symmetry, is that when you are non-committal about a hypothesis, you assign it a vague probability. So what you say is, well, the probability of this hypothesis is somewhere between 0 and 1, but I don't know where. So you're not saying that the hypothesis is improbable. You're not saying that it's 50% probable. You're saying, I just don't know, right? I don't know what probability to assign it. And this is Van Frassen's position concerning hypotheses about unobservables. Now, the point is that the Bayesian machinery can't do anything with vague probabilities like this. If all you can say is that the probability is somewhere between 0 and 1, but you have no further judgment than that, then evidence is powerless, right? In order to apply Bayesianism, you have to assign a specific prior probability. Now, of course, the Bayesian, or at least the subjective Bayesian, might say, well, this is no problem because prior probabilities, as we saw in the last video, can be anything you like, right? Due to washing out of the priors, we will converge, our probabilities will converge over time. So in those cases where you are unsure or non-committal or agnostic, right, you just choose any prior that you like and work with that. Just pick one at random and work with that. So, that's a perfectly reasonable, pragmatic solution. But the point is that if I do that, if I just choose a prior at random, then that prior probability does not represent my epistemic state. It doesn't represent my degree of belief. We can't say that, if I've just chosen a prior at random for a hypothesis about which I'm non-committal, we can't say that this probability just is my degree of belief. So, again, there's this problem. Now, could the Bayesian say, well, maybe it's a further rational constraint on priors that they must have a definite value? There's no obvious argument for that. It's not clear why assigning a vague probability, why simply being non-committal about a hypothesis would necessarily be irrational. Certainly, there's no Dutch book argument against this. A person who assigns a vague probability just wouldn't know what to bet, or maybe they take the bet based on a random procedure like flipping a coin or something. But there's certainly no basis on which to construct a Dutch book. What's powerful about the Dutch book arguments is that if you are susceptible to a Dutch book, you ensure a loss. You will definitely make yourself worse off. And it's immediately obvious why rationality requires us to avoid this. If we're susceptible to Dutch books, we'll be less able to achieve our goals. But vague probabilities, there's no Dutch book against it. It seems like the Bayesian has to resist vague probabilities because if we allow vague probabilities, the Bayesian machinery doesn't work. But that, of course, seems rather ad hoc. The same kind of difficulty actually arises in another way. So if somebody assigns a probability of 0 or 1 to an empirical hypothesis, that can never change in the face of the evidence. So again, applying the Bayesian machinery, no matter how much evidence you get, if you start off with a prior of 0 or 1, it will never change. It's entirely consistent with the probability calculus to be certain about the truth or falsity of an empirical hypothesis. There's no Dutch book argument against this position. The Bayesian has to rule out assigning 0 or 1 to empirical hypotheses, but it's not obvious how they do that. And it's also sort of not obvious what these probabilities mean if they're no longer representing people's degrees of belief. And I guess the point here is, Bayesianism seems like it starts from a very simple and straightforward foundation. If we assume that probabilities are degrees of belief, and then we follow the probability calculus, it looks like we get, Bayesianism, right? But actually, this claim about the connection between probabilities and degrees of belief needs various additions and adjustments to deal with uncertainty about logical truths, to prevent people assigning vague probabilities, to prevent people assigning 0 or 1 to empirical hypotheses, and so on. Okay then, so another problem concerns the Bayesian definition of scientific confirmation. Recall that for the Bayesian, E confirms H if and only if the posterior probability of H is higher than the prior probability of H. So confirmation on this view is simply a matter of increased probability. The evidence comes in and increases the probability of the hypothesis, and that's all there is to scientific confirmation. But is this right? Well, there are two ways really of putting pressure on this. First of all, there are cases where a fact causes the probability of a hypothesis to increase, but we wouldn't say that the fact confirms the hypothesis. And second, there are cases where a fact confirms a hypothesis, but without increasing the probability of the hypothesis. So let's take the first case, cases where a fact causes the probability of a hypothesis to increase, but it doesn't confirm the hypothesis. Here's an example. If I visit London, this increases the probability that I will run naked outside Buckingham Palace. But does my visiting London confirm the hypothesis that I will run naked outside Buckingham Palace? Well, that seems very odd, right? I mean, that doesn't seem to be a case of confirmation here. Now, I don't know, maybe the Bayesian can just bite the bullet on this one. So the Bayesian might say, well, look, there are degrees of confirmation. We saw this already with the example of the HIV test in the last video. The HIV test, as you recall, gave a positive result, but still, I probably don't have HIV. Nevertheless, the test does provide some confirmation to the hypothesis that I have HIV. It just doesn't sort of confirm it strongly enough to make it probably true. So maybe we could say something similar for this Buckingham Palace hypothesis. My visit to London increases the probability of the hypothesis and thereby confirms it. But the probability is still very, very low. It's still so low that it's not really even worth considering the hypothesis. So, you know, in most contexts, we wouldn't say that my visit to London confirms the hypothesis that I will run naked outside Buckingham Palace, just because we won't even be considering that hypothesis seriously. So maybe we can solve this sort of case like that. However, there are more difficult cases, I think, along similar lines. So let's consider a newly proposed hypothesis that is supported by general theoretical considerations and maybe a few experiments. There's debate among scientists whether this hypothesis is true, but again, it's very, very newly proposed. This is it's newly on the scene. Now suppose that this hypothesis is supported by an article that appears in a highly reputable scientific journal, right? Now, appearing in the journal increases the probability, or at least, that the hypothesis is true. Or at least it certainly increases my degree of belief in the hypothesis, let's say, because hypotheses that appear in reputable scientific journals are more often true than those that don't appear in such journals. So the fact that this hypothesis is supported by an article in a reputable scientific journal would probably increase my confidence in the hypothesis. So then it looks like the Bayesian has to say that appearing in the reputable scientific journal confirms the hypothesis. But surely that gets the situation the wrong way around, right? I mean, what's really going on is that appearing in a reputable scientific journal isn't itself evidence that confirms the hypothesis. Rather, it's an indicator that there is evidence that provides some confirmation to the hypothesis. So when I see that a hypothesis is supported by an article in a reputable scientific journal, that increases my confidence in the hypothesis because it indicates, it's a reliable indicator that there is evidence that confirms the hypothesis. So I mean, I guess the sort of point here is, look, there are all kinds of things that should raise my subjective probability in a hypothesis, that should make me more confident about a hypothesis. These include both the confirmation relation between evidence and hypothesis, but also various things that are merely indicative of the existence of confirmation between evidence and hypothesis. So appearing in a scientific journal indicates that hypothesis is confirmed by evidence, and it therefore raises my subjective probability that the hypothesis is true, but it isn't itself a form of scientific confirmation, obviously. Okay, so let's take the second case, the case where we have a fact confirms a hypothesis without increasing the probability of the hypothesis. So consider Newtonian mechanics. One of the great triumphs of Newtonian mechanics is its correct prediction of the path of Halley's comet. Now we know that Newtonian mechanics is false, right? It's been superseded by general relativity. And it seems like what we want to say here is there's a great deal of evidence for Newtonian mechanics, so that there are indeed a huge number of facts that confirm Newtonian mechanics. It's just that there's also decisive evidence against it. So, we can understand why people in the 1800s were so convinced that Newtonian mechanics was correct, because we can also see all of that confirming evidence, right? The evidence like the prediction of the path of Halley's comet. That's very powerful evidence for Newtonian mechanics. So what the Bayesian says, though, remember, is that confirmation is a matter of the evidence increasing the probability of the hypothesis. But if we know that Newtonian mechanics is false, its probability is 0, and that probability can never increase no matter how many correct predictions it makes. Now, in fact, this kind of thing is a problem for modern scientific theories as well, because many theories and models in modern science include idealizations, where certain properties of a system are intentionally misrepresented. For example, when modelling stars, the equation of state is often the ideal gas law, where an ideal gas consists of dimensionless particles whose movements are entirely random and that interact only via perfectly elastic collisions. We use this idealization because in certain circumstances, certain gases behave in approximately the same way an ideal gas would behave, but this idealization is just false, right? No real gas is anything like an ideal gas on the molecular level. It's not even approximately true to say that a real gas is composed of dimensionless particles. So we know then that central elements, central aspects of many of our models of stars are false, in which case there can't be any increase in probability. The probability of the model is 0, and no evidence that we acquire from studying stars can make that probability increase. Yet it seems that we still want to say that these stellar models can be confirmed by the evidence. So, this is quite a serious problem, because idealizations like this are ubiquitous throughout the sciences. Scientists constantly include these kinds of false assumptions in their models in order to make the systems tractable. And so it's not obvious how the Bayesian should handle cases like this. So when we think about all of these examples of where probability and confirmation seem to come apart, I wonder if what's missing in the Bayesian account is that confirmation is connected to testing. So, you confirm or disconfirm a hypothesis by conducting a test of that hypothesis. Like take the case of me visiting London. Although my visit to London increases the probability that I will run naked outside Buckingham Palace, it's not in itself a test of the hypothesis that I will run naked outside Buckingham Palace. So maybe that's why it doesn't seem to make sense to speak of confirmation here. Similarly, when a hypothesis appears in a scientific journal, that's not a test of the hypothesis. The paper in the journal will instead simply report tests that have previously been conducted. And finally, obviously we can set up tests of hypotheses that we know are false, and we can test models that include idealizations. We can use the false hypothesis to design an experiment and to predict a particular set of outcomes, and then undergo a test. And it seems like this sort of connection between confirmation and testing is what seems to be missing in the Bayesian account. Okay then, so one of the most famous problems for Bayesianism is the problem of old evidence. And this was presented, for example, by Clark Glymore in his paper Why I Am Not a Bayesian. So if you watched the video on novel prediction versus accommodation, you'll know what this problem is, but just to reiterate it, assume that E is some piece of evidence that we already have. For example, the value of the precession of Mercury's perihelion. This was a well-known anomaly for Newtonian mechanics during the 19th century. Mercury's orbit deviated from the predictions of Newtonian mechanics, and various hypotheses were proposed to account for this, but none of them worked. The problem was eventually solved in the early 20th century by general relativity. General relativity entails the correct value for the precession of Mercury's perihelion. Now, it's often assumed that this evidence confirms, at least to some degree, general relativity. In fact, the accommodation of Mercury's orbit was seen as one of the great triumphs of general relativity. So this looks like a case where a theory is confirmed by old evidence, by a fact that was already known before the theory was constructed. Now, recall the Bayesian view of confirmation, right? E confirms H when posterior is higher than the prior. And how do we work out the posterior? Well, we apply Bayes' equation. Now, at the time general relativity was proposed, Mercury's orbit was already known. So the probability of E equals 1. And in that case, if we assume that the hypothesis entails the evidence, the probability of E given H would then just be 1, then it follows that the probability of H given E is equal to the probability of H. So the posterior is equal to the prior. So E can't confirm H when E is already known. Old evidence can never confirm a hypothesis. General relativity receives no support at all from its accommodation of Mercury's orbit. Many people have found this to be a very unappealing result. Now, as we noted in the video on novel prediction, some people do accept this consequence. Some people accept that only novel predictions can confirm and old evidence can't confirm. But it does seem very counterintuitive. Even if you think that novel prediction is in some way superior to accommodation, surely accommodation of old evidence can provide some degree of confirmation. Certainly, most scientists think that accommodation is important. So what can the Bayesian say about this? Well, one response is to just bite the bullet and accept that old evidence can't confirm hypotheses. But we could say that this isn't as serious a problem as it seems. According to Bayesianism, when a new hypothesis is proposed, you have to assign a prior probability to it. And for the subjective Bayesian, as we've seen, there are no rational constraints on priors beyond conformity with the probability calculus. So you can assign a prior on the basis of old evidence. You might find relativity's accommodation of Mercury's orbit very impressive, and you assign a high prior on that basis. That's fine, right? So the accommodation doesn't confirm the theory, but it may be impressive. It may have a lot of psychological power. You may feel that the accommodation is a very positive feature of the theory, and so you assign it a high prior on the basis of its accommodation of old evidence. Of course, this isn't really a solution to the problem so much as a dismissal of it, and given just how much accommodation of old evidence has figured in the evaluation of scientific theories historically, we might insist that any confirmation theory that doesn't account for accommodation of old evidence is lacking in some way. Also note that this response isn't going to work for cases where the accommodation is made long after the theory is proposed. For example, if general relativity had been proposed, but then it took many years before its accommodation of Mercury's orbit were discovered, in that case, the prior would already have been assigned. Okay, so another response to the old evidence problem is that in the case of old evidence, it's not exactly that E confirms H, right? So H is not confirmed by E. The hypothesis is not confirmed by the evidence. Rather, what confirms the hypothesis is the fact that the hypothesis entails the evidence. So we learn this logical fact. We learn the logical fact that H entails E, and then we conditionalize on this, and the conditionalization increases our degree of belief in H. So in a way, on this response, the Bayesian adopts a kind of disjunctive view of confirmation. When the hypothesis entails the evidence and the evidence has not yet been acquired, so it's new evidence, then the evidence itself confirms H, right? The evidence confirms the hypothesis. When the hypothesis entails the evidence and the evidence is old evidence, then learning the fact that the hypothesis entails the evidence is what confirms the hypothesis. So, we would say that the probability of the hypothesis, given that the hypothesis entails E, is greater than the probability of the hypothesis. So one way to look at it is like this, right? So whenever H is confirmed, two things must be true. A conjunction must be true. So first, it must be true that H entails E. And second, it must be true that E, right? Now, in the case of a novel prediction, we already know that H entails E. We've already worked out that we should expect to see E if H is true, and then we observe E, and this is what raises the probability of H. In the case of accommodation of old evidence, we already know E, and then we discover that H entails E, and this raises the probability of H. In both cases, we make a discovery that allows us to assert both that H entails E and E. Right? It allows us to assert the whole conjunction. And so maybe that's one way we might try to solve this problem. Now notice that, like the previous response, this response concedes that old evidence doesn't really confirm any hypotheses. So when we say, we might say, speaking colloquially, that general relativity is confirmed by the precession of Mercury's perihelion. But in fact, what confirms general relativity is not the precession of Mercury's perihelion, but the logical fact that general relativity entails the correct value for the precession of Mercury's perihelion. So the obvious problem with this response is that it runs right into the problem of logical omniscience that we discussed earlier. If probability assignments are to conform to the axioms of probability theory, then the probability for logical facts, such as the fact that H entails E, should be 1. So the Bayesian can only give this response to the problem of old evidence if they can make sense of uncertainty with respect to logical facts. I think it's also worth noting that this response doesn't apply to cases where a theory is explicitly constructed so as to entail a piece of evidence. For instance, Mendeleev intentionally constructed his periodic table to fit the facts about elements known at the time, and many scientists held that his accommodation of these facts provided good reason to believe his theory. He also made some novel predictions as well, but the accommodation of known facts was considered to be at least some reason to believe his theory. But in this case, the hypothesis was explicitly designed to entail the evidence. So obviously, nobody ever, it wasn't new information. We didn't learn new information that the hypothesis entailed the evidence. It was known from the start. So this response isn't going to deal with cases like that. Okay, so a more popular response to the problem of old evidence is the counterfactual response. The idea here is that when we apply Bayes' theorem, we shouldn't consider the scientist's actual degree of belief in E. Instead, we must consider what her degree of belief would have been had she not known about E. So basically, we should conditionalize on E as though it had not yet been observed. We set the probability of E to be what it would have been had E not come to light, right? So, so in that case, the probability of E does not just equal 1. Now notice that, unlike the previous responses, on this response, the evidence really does confirm the theory. So this response does preserve our intuitions about confirmation, right? General relativity really is confirmed by the precession of Mercury's perihelion. So we're told to set the probability of E to be what it would have been had E not been observed. The obvious question is, well, how is that supposed to work? How do we know what this is? And when we try to work out how exactly to spell out this idea, we do run into some problems. The most straightforward way to do this is just to imagine removing our knowledge of E from our current stock of knowledge. So we just imagine removing our knowledge of the advance of Mercury's perihelion while keeping our other knowledge intact. So we just say, what probability would we assign to the precession of Mercury's perihelion if we didn't know about it? Now, the trouble with this is that there is currently now a whole host of other evidence that confirms general relativity. So we would put a fairly high probability on its prediction of the advance of Mercury's perihelion. After all, if somebody were to derive a new prediction from general relativity, let's say they were to make some prediction about, I don't know, the distribution of dark matter in the center of galaxies or something, you'd probably expect that prediction to be would be true, because general relativity seems to accurately describe things at least at that sort of scale. General relativity has been confirmed so strongly at this point that its predictions will now have a fairly high probability. So if we just imagine removing our knowledge of the advance of Mercury's perihelion, and then we're asked, what probability would we assign to it, we give it a very high probability. So in that case, the probability of E would not be 1, but it would still be very high, and so it would have very little confirmatory power. As we saw in the previous video, the more probable evidence is, the lower its confirmatory power. And in any case, it's hard to see how it really makes sense to sort of delete one item of knowledge while leaving the rest intact. I mean, surely, if we were to remove our knowledge of Mercury's orbit, that would inevitably alter some of our other beliefs as well. So, an alternative option for the counterfactual response is to do a bit of counterfactual history. We imagine a history of science where the advance of Mercury's perihelion was unknown into the 20th century. General relativity is proposed and it predicts a value for the advance of Mercury's perihelion. The value is then observed. In this counterfactual scenario, scientists can apply the standard Bayesian machinery. Before the observation of Mercury's orbit is made, the probability of relativity given value for Mercury's perihelion is greater than the probability of relativity. Right, the posterior is greater than the prior. So the Bayesian machinery works fine in this counterfactual scenario. Coming back to the real world then, the idea is that when applying Bayes' theorem, we take the value for the probability of E, for the probability of the advance of Mercury's perihelion, that the scientists in this counterfactual history used. So E confirms H, because if E had been acquired after H was developed, it would have confirmed H in this counterfactual history. Again, there are some obvious difficulties with this response. So in the counterfactual scenario where scientists had not discovered the advance of Mercury's perihelion in the 19th century, science must have been very different indeed. Mercury's perihelion was, in the real world, a major problem for physicists and astronomers in the 19th century. So, if we're imagining a sort of counterfactual history where scientists didn't know about this, how can we possibly know what this community of scientists would have thought of general relativity, or what their probability of the advance of Mercury's perihelion would have been? How can we possibly know what their probability of assignments would have been, or what their other evidence would have been? Surely there's just no fact to the matter. In any case, just a more straightforward problem here is that surely different scientists would have had different probabilities in our counterfactual history. Remember, probabilities for the Bayesian are just degrees of belief, and scientists can disagree. Bayesianism allows for a great deal of disagreement, especially in the early stages of theory development. Indeed, that was supposed to be one of the virtues of Bayesianism, right? It allows for a lot of rational disagreement at first, and then convergence occurs over time with the washing out of the priors. So imagining, general relativity early in its development, if we imagine this kind of counterfactual history, it looks like there wouldn't have really been any consensus on the probability of Mercury's perihelion advance. Some of the scientists in this counterfactual scenario would have found general relativity very attractive, and so would have assigned its predictions at high probabilities. Other scientists would have found it implausible, and so assigned its predictions at low probabilities. There wouldn't have been any consensus on the probability of E. So the problem of old evidence remains one of the most serious problems for Bayesianism. Actually, before leaving the problem of old evidence, it's worth noting that there are actually other versions of it. It has been extended, as it were, applied in new ways. So consider a novel prediction of a theory. For example, general relativity's prediction of the value of light bending around the sun. The value of light bending was not known when Einstein proposed his theory, and most scientists would have put its probability as being fairly low. So when that value was discovered, it was new evidence, and it had a lot of confirmatory power according to Bayesianism. When we realised, that general relativity made the right prediction about the value of light bending around the sun. That was something new and surprising. It was a very powerful, novel prediction. So that's the case for Einstein's contemporaries. But what about for us, right? I mean, so like for us, the value of light bending was discovered before we were even born. It's not new evidence for us. Again, then, it looks like, for us, the value for light bending, the probability of light bending is just 1. And so, again, can't confirm any hypothesis. It can't confirm general relativity. But that's surely absurd, right? I mean, surely general relativity is confirmed by the value of light bending. So this is sometimes called the problem of old new evidence, because the new evidence of light bending is now old, and so it can't have any confirmatory power. So basically Bayesianism can't accommodate confirmation relations between hypotheses and evidence that are both well established. Since confirmation is just a matter of increased probability, it seems to be indexed, as it were, to particular people at particular times. Confirmation for the Bayesian is only possible when the posterior is greater than the prior. That's what confirmation is, right? The posterior probability is greater than the prior probability. But recall the slogan of Bayesianism, that today's posterior is tomorrow's prior. So evidence that has confirming power today is powerless to confirm tomorrow. So this, again, is a very odd result. Okay, so fourth problem for Bayesianism. Some philosophers have questioned even the more technical aspects of Bayesianism, in particular the application of Bayes' theorem when working out posterior probabilities, the probability of a hypothesis given a piece of evidence. So here's an interesting example from Deborah Mayo, who argued against Bayesianism in her book Error and the Growth of Knowledge. Consider Isaac. Isaac is a school student who takes a college readiness test and he achieves a very high score. Call it X, right? This score of X is very rarely achieved by people who are not ready for college. Let's say that 99% of people who achieve X are in fact ready for college. Now Mayo says Isaac's score of X is good evidence for the hypothesis that Isaac is ready for college. And this is because Isaac passed a severe test. A severe test is a test that a hypothesis is very unlikely to pass if it's false and very likely to pass if it's true. So when a hypothesis passes a severe test, we can expect that it will similarly be successful in the future in predicting experimental outcomes of tests. The college readiness test is a severe test. It's very improbable that a person who is not ready for college will pass the test. So Isaac's score gives us good reason to believe that Isaac is ready for college. So says Mayo. So why is this a problem for Bayesianism? Well, in this example, the Bayesian will object that we are neglecting the base rates of college readiness. Let's imagine that Isaac comes from a severely underprivileged town. Mayo calls it few ready town, where, as a result of poverty and discrimination and so on, very few people are ready for college, say only 1 in 1,000. So the prior probability that Isaac is ready for college is 0.001. Applying Bayes' theorem, the posterior probability of his college readiness after the test is still very low. Now notice that this is structurally similar to the HIV case that we examined in the previous video, right? The point there was that due to the very low rates of HIV in the population, a positive test result does not provide good reason to believe that I have HIV. And the Bayesian will draw a similar conclusion about Isaac. Despite Isaac's positive result, he's probably not ready for college. But is this right? So the Bayesian is claiming that in order for Isaac to qualify as ready for college, he would need to achieve a much higher score, right? So in general, people from few ready town need to achieve a much higher score than people from more affluent towns. The Bayesian concludes that Isaac is not ready for college on the basis of exactly the same performance that would lead her to conclude that a person from a more affluent town is ready for college. But why? I mean, surely the evidence of a person's readiness for college is in their performance on the test, not the population from which they come. I mean, worse, the Bayesian here seems to be outright discriminatory, right? I mean, we know in the real world that disadvantaged communities produce lower proportions of well-educated people. So should universities and colleges start discriminating against people from such communities? Should universities require that they have higher grades than people from more affluent communities? Now, I mean, the Bayesian might say, well, look, we're dealing here with epistemology, not ethics, right? And Mayo is telling us to ignore the population from which Isaac came, which, given the population differences in college readiness, is effectively telling us to ignore a relevant factor to Isaac's college readiness. Yes, sure, in practice, we shouldn't discriminate people on this kind of basis. But, if we're just talking about the epistemology, we'd have to say that, there is a lower probability that Isaac is ready for college. So maybe the Bayesian might sort of take that kind of line here, but Mayo says the problem is that the Bayesian is committing a fallacy of her own, right? So Mayo says the Bayesian is committing the fallacy of instantiating probabilities. So we can take a well-defined probability, right? So a population where X% of the members have some property P. If this is the only information that we've been given, then if all we know is that an individual is in that population, we can say, well, there's probability X divided by 100 that this individual has property P, right? So in other words, if we randomly select an individual from that population, then given this information alone, we would say there's probability X divided by 100 that they have property P. Now, as an abstract model, this is fair enough. The probabilities are well defined within this model. The fallacy of instantiating probabilities occurs when we attach this probability to a real individual independently of the model. And the reason why we can't do this, the reason why we can't sort of to attach the probability to a real individual is because there are all kinds of populations to which the real individual belongs. So this is, I guess, the trouble of defining reference classes that we mentioned in the previous video. We can't infer that Isaac's prior probability of college readiness is 0.001 from the fact that 0.1% of people in his town are ready for college, because there are no grounds for taking the population of the town as the relevant reference population. Isaac is a member of many populations. He's a member of the population of the town, the population of the country, the population of people taking the college readiness test, the population of people with blonde hair, let's say, whatever. So in each of those cases, there are going to be different base rates of college readiness. So for Mayo, then, there really is no prior probability of Isaac's college readiness. Isaac's college readiness is demonstrated by the test, and we can speak of probabilities only for experiments or other sort of processes or test situations with well-defined outcomes. Now, maybe the subjectivist Bayesian might, object here that the whole, one of the fundamental claims of at least subjective Bayesianism is that prior probabilities are unconstrained. So actually, we don't have to take our priors by considering the base rates of college readiness in the population. I mean, we could just pluck a prior out of thin air. But, we might just say, well, we'll assume that the prior probability of each person's college readiness is, it's the same for everyone, taking the test. But I think the sort of broader point here is that the prior probability of the hypothesis, if it even makes sense to talk about the prior probability of the hypothesis, doesn't really matter. So we may think that Isaac probably is ready for college, or we may doubt him, or we may just be unsure, we may just be non-committal. Give him the test, right? And we look at how well he does on the test, then we can specify the probability of his college readiness. What confirms the hypothesis that he's ready for college is that this hypothesis passes a severe test, not that the posterior probability is higher than the prior probability. In fact, I suppose the very fact that prior probabilities are totally unconstrained, the fact that they can be just anything you like, would perhaps indicate that they are not really relevant. That they're not worth considering. So for Mayo, what matters are severe tests. Scientists construct severe tests of hypotheses, and a hypothesis is confirmed when it passes a severe test. So a HIV test that we mentioned in the last video, that HIV test is a severe test. And so in that case, it looks like, is Mayo going to have to say that the HIV test would confirm the hypothesis that I have HIV, or would give us good reason to believe that I have HIV? The Bayesian insists we have to take into account the base rate of HIV in the population, and surely there is something right about that. If we were to give HIV tests to everybody indiscriminately, then most of the positive results would be false positives. If I were to get a HIV test today, just randomly, then, if the result were positive, it would probably be a false positive. And isn't the point here that, well, the base rate is so low in the population that most of the positives are going to be false positives. So it seems like the Bayesian is at least on the right lines here. But I guess the point is that we don't just kind of indiscriminately give out HIV tests to everybody. You're only given a HIV test if you have, other symptoms, or if you engage in high risk behaviours. I think usually is, if you are engaging in a high risk behaviour like injecting heroin, right, then you might be given HIV tests. So we don't really need to define a reference class and work out the base rate of HIV in the reference class. We know that if somebody is engaging in a high risk behaviour like injecting heroin, the HIV test is a very effective indicator, a very reliable indicator of HIV. That's what matters. The point of all of this, Bayes' theorem follows from the axioms of probability theory, as we saw. And as a piece of mathematics, it's completely uncontroversial. But how do we actually apply it? When we ask about the prior probability that Isaac is ready for college, or the prior probability that I have HIV, how do we define the reference population for which the base rate has to be calculated? For Mayo, the Bayes' theorem is not really all that useful for determining the bearing of evidence on a hypothesis, because the prior probabilities can't be specified. So, those were some of the objections to Bayesianism. Obviously there's Bayesianism has a huge literature, there many more objections to it, and there are many more reasons why people might favour it. But hopefully that's given you a sense of the sort of overall shape of the debate. And that's all. So thanks for watching. Goodbye.